Today we will start a new chapter, that is etching. In a lithography process, the next step will be the etching. All VLSI process, when you are going to define certain windows, etc., just after lithography, etching follows. Next step. The etching is a process by which patterns are transferred by selective removal of unmasked portions of a layer. By lithography, we covered some of the areas on the substrate or on film, and some of the areas are directly exposed to etching solutions. So that means the unmasked region will be etched by etching solution. And what is the masking layer here? That is the photoresist. Photoresist is a protective layer. So those regions which is covered by the photoresist, those regions will not be etched. Okay. So now in etching process, we have to think an etching medium. That medium should not react with the mask material. Mask material in this particular case is photoresist, but it may be other also. At the same time, the etching medium should not interact or react with the substrate material. After the film is completely removed by etching, then what is the end point? End point is the substrate. For example, in all diffusion or implantation cases, we want windows to be opened, and this window we open in silicon dioxide. Silicon dioxide is used as a mask material. Then we do the lithography, and lithography process, some region is covered with the resist, and windows region we get the exposed silicon dioxide, and this silicon dioxide is etched, and then what we do, we remove the photoresist, then the window is available for diffusion or implantation. So that means when we are going to etch silicon dioxide, then that particular etching solution or etching medium should not react with photoresist, number 1 point. Second point, as soon as silicon dioxide etch is over, then below silicon dioxide what is there? Silicon. So that particular solution should not attack silicon. Okay. So that means 2 points you have to remember. The etching medium should not react with the mask material, and here the mask material is photoresist. And the second point is the etching medium should not react the substrate itself. So there are two types of etching mechanism. One is known as wet etching, and other is known as dry etching. In wet etching, the unmasked layer is removed by selective liquid etchants. Wet means we are using liquid etchant, and again I use selective word. The reason is the liquid etchant selectively removes the film, not the mask material and the substrate material. That's why I mention here selective liquid etchant. Whereas in case of dry etching, plasma is used in the form of low pressure gaseous discharges to remove unmasked layer. The dry etching, its another name is plasma assisted etching. the main difference between wet etching and dry etching is the etch medium in wet etching is a liquid, but etch medium in dry etching process is a plasma. Examples of dry etchings are plasma etching, sputtering, RIE, which is known as reactive ion etching, IBE, which is ion beam etching, and RIBE, reactive ion beam etching. In both cases, means in case of wet etching and dry etching, a reaction will take place between the etching medium and the film. A chemical reaction will take place between the etch medium and the film to be etched, and the reaction product should be such that either the reaction product evolved as a gas or the reaction product is soluble in the etch medium. Otherwise, you cannot remove the film. The film to be etched will react with the liquid and it will form some compound, and that compound must be dissolved in the solution, means in case of wet etching, in the liquid etchant solution. In case of dry etching, the reaction will take place, means plasma and the film to be etched. Chemical reaction will take place, and the reaction product should be such that it is volatile in nature. If it is a gaseous volatile, so it will be taken away by exhaust system. So that means the film is removed. So that should be the basic principle in etching mechanism. Now we will discuss some of the features of wet etching process. Wet etching is a practical alternative for a high throughput flexible production process. High throughput is an important point. Why it is an important point? Because in any production level, commercial production industry, if the throughput is not high, it is not economic. And in wet etching, you can perform in a batch. A batch of say 25 wafers or a batch of 40 wafers can be etched simultaneously in a etching tank. So per wafer etching time is small. You can have more wafer etched in a particular time, and wet etching process is a flexible production process. Next point is etch reactions with primary film are made thermodynamically favored over reactions with other films by proper selection of etch chemicals. I discussed this point. Primary film means film to be etched. In case of resist silicon dioxide silicon system, primary film should be silicon dioxide. In case of aluminum patterning, primary film should be aluminum film. So that is the primary film. Primary film are made thermodynamically favored over reactions with other films. That means you cannot ensure that the etching medium will not at all react with the mask material or with the substrate. For example, if you use buffer hydrofluoric acid to remove silicon dioxide or to etch silicon dioxide, you cannot ensure that buffer hydrofluoric acid will not react silicon underneath silicon, or you cannot 100% ensure that this buffer hydrofluoric acid will not react at all with the photoresist film. Photoresists film is made such that it should not react, but the fact is that buffer hydrofluoric acid also etches silicon, but it is not thermodynamically favored. That means at a particular temperature, if you do the etching reaction, the etching of silicon dioxide and buffer hydrofluoric acid is etch rate is extremely high compared to the etch rate of silicon and buffer hydrofluoric acid, and that is done by buffering the hydrofluoric acid by using some ammonium fluoride, because hydrofluoric acid, water and ammonium fluoride are mixed in a certain stoichiometric ratio to have this buffering action. What is that buffering action? That means it will etch silicon dioxide, but it will not etch silicon. So that is the selectivity. This is a very important point. Okay. So you have to etch, you have to select the etch chemicals properly so that this property is maintained. Most wet etch reactions involve oxidation reduction. By oxidation reduction reaction, the byproduct, sometimes you get the oxides or hydrides, something like that, hydrogen reduction reaction, sometimes oxidation reactions, and those are dissolvable in the liquid. That is the main emphasis of that particular point. Now, there are two basic wet etching techniques, namely immersion etching and spray etching. We are now discussing only on wet etching process. Immersion etching is very simple. What do you do in immersion etching? In immersion etching, the batch of wafers are put in a container which is filled with etching solution. The complete batch is immersed into the etching solution in a container. When the masked or unmasked wafer is submerged in etching solution, then the etch solution will react with unmasked region of the film, and this reaction will be promoted by mechanical agitation. If you give some mechanical agitation during wet chemical etching, the etching will be uniform over time. What is the reason? Let me explain this point. During reaction with the etching solution and the film, I told you that oxidation reduction reaction will take place. So there some amount of gas will be evolved, either oxygen or hydrogen or nitrogen, depending on the material. If you have silicon nitride, is expected the NO2 or N2 gas is evolved. If you have silicon dioxide, expected the oxygen gas is evolved, something like that. Sometimes the H2O molecule will evolve. So those gas molecules will stick on the surface of the film, and if those gas molecules stick as a bubble on the surface of the film, then they will prevent the contact of the etching solution with the film material. A layer of gas bubbles will always prevent the etching solution, liquid etching solution, to come in close contact with the film. The reaction will be hampered. Now, if we give some mechanical agitation, then what will happen? Those gas molecules will not get chance to form bubble on the surface of the film, and that will evolve as a bubble through the gas and in the ambient. They will not settle on the film if we give a mechanical agitation. That means stirring. If you in the solution is stirred, or if you give a mechanical agitation, then no scope of accumulation of the gas bubbles, gas molecules on the surface of the film, and then you can ensure uniformity and constant etch rate. Is clear? That thing you might have seen in case of the H2O to H2SO4 reaction in case of cleaning you have done in the laboratory, and as soon as H2O and H2SO4 1:1 is put, then immediately if you put the silicon wafer, you see vigorous reaction will be there, and nascent hydrogen will be there, and that will stick on the surface of the silicon wafer, and the silicon wafer will have a tendency to float on the liquid because it is light. All the gas molecules will stick on the surface. Have you seen it? It will float, and that's why always some agitation is given in the liquid as well as total system, so that the gas molecules cannot settle on the surface of the wafer, but is evolves as a gas into the ambient. So in all immersion etching, a mechanical agitation helps to get uniform etch rate and constant etch rate. Next is spray etching. Spray etching requires less volume of chemicals and is faster than immersion etching. And in this particular technique, we spray the liquid etchant on the surface of the wafer. So if you spray it, no need of giving again mechanical agitation. Spraying means automatically some agitation is there. With a certain flow, we spray through the nozzles the etching solution, and the wafers, if you agitate is well and good, no problem. The agitates are the wafers are kept on the wafer holder, and if you give a movement or rotate, for example, and the whole thing is kept in a etching chamber, and etching chamber what is done, there some axle is there, and there the wafers are kept and whole thing is rotated, and from the wall of this etching chamber the etching solution is spread over the entire wall. So the wafers are rotated and etching solution are spread over the entire chamber, then the liquid which is coming out, that is also ejected from the chamber. So this is the technique in spray etching. So here requires less volume of chemicals, because in immersion the whole container is filled with the etching solution. If it is a big container, you may require say 2 liter or 3 liter of etching solution at a time, but here you don't need it. And this spray etching is faster than immersion etching. And another good advantage of the spray etching is that fresh etchants is constantly supplied to the wafer surface while the etched products are continuously removed. Is a very important point. In immersion etching, when the wafers are immersed into the liquid, during reaction etched products will form. That means as more and more reaction progresses, more and more etched product will form, and those etched product will be dissolved in the liquid. So the strength of the etching solution will degrade with time, because the etching solution is consumed, etched product is formed, and that is dissolved in the etching solution. That means strength is going to be lower and lower with time, and the whole solution you are not taken away during the etch process. But here you see, in case of spray etching, the fresh solution is sprayed, and during reaction etched products will be formed and they are taken away. Again fresh, because through the nozzles always fresh etching solutions are coming. That means the wafers throughout the etch time they are getting fresh solution, and because of that during the etch time the etch rate will be uniform. You can ensure that. For example, if a particular film, if it takes 10 minutes to etch, so initial 2, 3 or 4 minutes the etch rate, and if you find at the 9th and 10th minute etch rate, that will not be the same, because the strength of the solution is going to reduce with time. That is not in case of spray etching technique. And etch products are continuously removed from the chamber. So that is one advantage in spray etching. Good process control and etch uniformity are easily obtained from spray etching. In industrial environment, now that means in production environment, we always prefer spray etching compared to the immersion etching. In VLSI processing, because of different reason, people go for the dry etching process. They are avoiding wet etching, and those problems we will mention in future slides. But very recently it has been observed that there has been a resurgence of wet etching for certain process steps, because plasma etching fails to provide the required etch selectivity, damage-free interface, and particle contamination-free wafers. Although people prefer dry etching or plasma etching for VLSI processing, even then, in some cases, finding proper etching medium, etch gas is difficult, and so people prefer in some cases wet etching. One of the aspect is etch selectivity, because if you don't get any dry etch medium, dry etch means the etch medium will be gas plasma. If you don't get proper plasma which will have proper selectivity, that means it will, in case of silicon dioxide and silicon both etches in the same rate, then you are in a problem. If the photoresist and silicon dioxide both are etching at the same rate, then you will not have any selectivity, both things will be etched out. So that selection in some cases is very difficult. Finding etching medium is very difficult. In those cases you may get liquid etching very easily, and that can satisfy your requirement. And another problem of the wet etching, another problem of the dry etching is the damage, because in the plasma etching there is a high chance of forming damages on the surface of the silicon wafer, but in wet etching technique the damages are less, very less. Now I will discuss on two techniques of pattern transfer. One is known as subtractive, another is known as additive method. Subtractive and additive method. Subtractive method is normal lithography technique, and additive method is something different from normal lithography technique. Here the approach is different. If you compare the process steps in case of subtractive and additive method of pattern transfer, you see in case of subtractive pattern transfer, initially on substrate the film is formed. The film is maybe a metal film, maybe silicon dioxide. That is the film which you want to be etched, okay. So that film may be silicon dioxide or metal or whatever it is. Now in a normal lithography technique, what you do, you put a mask using lithography technique. The mask is photoresist, so covered a certain region by photoresist, and then this is the unmasked region and this side is unmasked. Now you etch it. During the etching the film will be etched here and here, unmasked region film will be etched, and the masked region the film will be protected from the etching solution or etching medium, and at the end you remove the photoresist by photoresist remover and you will have this pattern. only the film is here, only this portion where it has been masked. The mask side is here and the film side you are getting here after removal of the mask. This is the normal lithography and etching technique. Okay. Now, if you look into the another method which is known as additive method, what is done here? On the substrate, we have not deposited the film. If the film is a silicon dioxide, without silicon dioxide or without, if the film is metal, without deposition of metal, initially you do the lithography. Photoresist is coated and using the mask it is exposed and developed and you get the pattern something like this. And here the mask region is different from the earlier one. In the earlier one you have masked in the central region here, you see. In the parallel side diagram you can see here you have masked the opposite regions, that means complementary region I can say. The middle is not masked and two sides are masked. Now what you have to do now you deposit the film. That film, as I mentioned, maybe oxide or maybe metal. So that film is deposited after lithography is over. Lithography and development is over. So the metal film will deposit on this mask layer, it will deposit on substrate layer and on in deposit also on the mask layer here in this region. Now what you can do, you can just using the photoresist remover solution or the mask remover solution. If the mask is different from photoresist, then obviously that mask remover solution. Then what will happen? I am not using the film etching solution. I am using the mask removal solution, remover solution. So now this yellow region is the mask, means say photoresist. So this photoresist here is removed, photoresist here is removed. So as the photoresist in these two sides are removed, automatically the film which was there on the top of the resist, that also will go away. If you remove the film, the photoresist here and here the yellow portion, the saffron portion, that color, that is the film, that also will go away. So what we will get ultimately? You are ultimately getting this pattern. So at the end we found the same pattern you are getting, but technique is different. Now you may ask, since you got the same pattern, why the second approach is used? First approach is a subtractive method, is a conventional one, we can go for that. Why the second one? There is obviously certain reason of the second method of pattern transfer, or namely the additive method of pattern transfer. What is that? What is the importance of that? The thing is that you see here I have not used the film etching solution. This is the important point. I have never used the film etching solution, but in this first technique, subtractive method, you need the film etching solution as well as photoresist remover solution. Both solution you need here. But in the second method, I have used only photoresist remover or the mask remover solution. I have never used film remover solution. That means in some cases you may have to pattern a film whose etching solution is not known. You don't know the etching solution, or even if you know the etching solution, that etching solution may affect the masking layer. Let me give you one example. For example, if you want to pattern a gold film, what is the etching solution of gold film? Aqua regia. Okay. So the aqua regia is a very strong etchant solution. If you use the masking layer as a photoresist or other metal film, so the aqua regia will react with those photoresist and other masking film. So you cannot pattern gold by etching aqueous reagent. The whole gold and as well as the masking layer will be dissolved by the aqueous reagent solution. Similarly, if you want to pattern say tungsten film, or you want to pattern say molybdenum film, etc. The etching solution of molybdenum or etching solution of tungsten will attack also the masking layer photoresist, then you cannot get the pattern. In those cases, you can easily use this additive method of pattern transfer, where you do not bother of the etching solution of that particular film, because we are not using any etching solution of the metal film. Here is the advantage, and similar situation we face in case of VLSI processing many times. But one of the important methodology in additive process is that the relative thickness of the metal film and resist film. I am explaining this point, try to understand. Here you see, after patterning the mask, means resist, by lithography technique, I have deposited the film. Now, if the film thickness is more than the resist, then here the film thickness will cover, it will come up to this point, and this will cover, it is very thick here. Look at the figure here. So now, if the film thickness, that means this saffron region color, so that height is more than the resist film, then this gap and this gap is not available. In that condition, the liquid etchant cannot attack the mask layer, that means resist layer, from this path and at this path also. For example, the side path here and these are not available, because it is continuous path. The masking layer will be reacted by the what? By the resist removal solution through this path and this path. If I don't allow this path, then this is not dissolved, resist film is not dissolved, and then automatically this film will not come out. That means this film and the film on the resist and the film on the substrate should not cover the side wall of the resist. If it is a thick enough, so there is no window here and there, that means the resist film will not be attacked by the removal solution and you will not get the pattern transfer. This is very important point when you do the lift off technique. This particular technique is known as lift off technique. Additive process, another name is lift off, because you are lifting the photoresist off along with the metal film or the film which you want to pattern. Okay. So here always the photoresist thickness should be larger than the film thickness. That means in lift off technique of additive method of pattern transfer technique, you cannot use photoresist which is less viscous. Thicker photoresist has to be used, and spin speed has to be very low, so that you can get larger thickness of resist film over the substrate material. So normal subtractive method and additive method, the photoresist spinning or the photoresist layer formation you have to take care of, so that larger thickness of resist film is obtained, and that is, and the metal film or deposited film is thickness is less compared to the resist. Now this process you can define by this. In case of subtractive method, film is deposited, these are steps, deposited, a pattern masking layer is generated lithographically, unmasked portion of the film is removed by etching. In case of additive method, what we do? Lithography mask is generated initially, film is deposited over the mask and substrate. The film over the mask are removed selectively by dissolving the mask layer in an appropriate liquid. The whole technique is also named as lift-off technique. In a nutshell, the steps can be written like this. Okay. Using lift-off technique, you can form a very small filament of any metal by certain under-etch over-etch technique. So that is I will discuss later on. Now, resolution and edge profiles in subtractive pattern transfer. The subtractive pattern transfer is a normal technique normally we use, and we will discuss some of the features of the subtractive pattern transfer. One of the feature is the resolution. The resolution of an etching process is a measure of the fidelity of pattern transfer, which can be qualified by two parameters, namely bias and tolerance. Bias is defined as the difference in lateral dimension between the etched image and the mask image. Etched image and mask image, a gap in the mask level, and when that gap is transferred into the photoresist or in the film, then what is the gap? That gap may not be exactly equal. The difference is known as bias. The difference in lateral dimension between the etched image and the mask image is known as bias. Tolerance is a measure of the statistical distribution of bias values. A zero bias process produces a vertical edge profile coincident with the edge of the mask. What is that? It is coming from the bias definition. What is the definition? The difference in the lateral dimension in etched image and the mask image. If the difference is 0, then bias is 0. That means ideally the mask image has been transferred on the etched image. If it is exactly equal the lateral dimension, then bias is 0. Obviously, that is the ideal condition that we always want it. Okay. So bias 0 means it will produce vertical edge profile. These are two parameters which decides the resolution of any etching process. Now, let us see what is bias. If you look at the diagram, then you can see the yellow region is here the mask, and the saffron color is the film. That film may be silicon dioxide, and the greenish color is light green color, so that is the substrate material. So the substrate, then film, and the top is the mask. Now, the lateral dimension between two mask portion on the to opaque region is a dm. Dm is a transparent region here in the mask. We want to find a window of lateral dimension dm on the film. But what will happen here, you see, because of the etching mechanism, isotropic nature of the etching mechanism, the etching medium will etch vertically downward, and after that it can etch laterally also, because it is isotropic in nature. Etch rate in the vertical direction, etch rate by the etching medium, that medium may be liquid, that medium may be plasma. If I concentrate on wet etching, then the liquid etching medium will etch vertically at a rate, and if that etch rate is same in the lateral direction also, in this direction, then you will get the etch profile like this. If the mask dimensions are like this, a small gap is maintained dm, and that dm in the mask level, the lateral dimension, and then we will have the film level after etching, the dimension is df, because the liquid etchant will etch in this direction, it will etch in this direction, it will etch vertically also, and all the etch rate is uniform. Then in the lateral direction here, how much will be the length of etching? Same length of the film thickness, because what are the film thickness from here to here? Same thickness, same distance will be etched laterally also. Okay, this is known as the undercut. Ideally, it should be vertical to this mask level, but under the mask something has been cut. It has been etched. It is known as an undercut. So, what is the bias? Bias definition is df in the film, the lateral dimension, dm is the lateral dimension in the mask layer. So, df minus dm is known as b, which is the bias, and this b is equal to 2 into undercut. Here is one undercut and here is another undercut. This undercut are same in left side and right side also. So, that means the bias b is equal to df minus dm, which is nothing but 2 into undercut, and this undercut is basically the thickness of the film, because it etches, you try to understand, etches here up from this point to vertically downward, at the same time from this point is laterally also. Whatever it will etch in this direction, same length it will etch in this direction. So, that means the bias also can be written as 2 into undercut, or undercut is basically the film thickness. In the other diagram, if the mask is different, then it will etches from the left side and right side. In order to have dm, if the mask level dimension at the bottom, you are getting basically here is a df. Then here the difference is again df minus dm is negative. Since it is the mask design is opposite, so you are getting negative. So, that is why bias value, we take the value is magnitude, not positive and negative. Magnitude. Here it will be positive in this case, and here it will be negative, but this relation is same. Here also, it is 2 into undercut, 2 into undercut, because here it also is etching laterally, and other side it is also etching laterally. So, it will be bias equal to 2 into undercut. Okay. Now, etch bias is a measure of the amount by which the etched film undercuts the mask at the mask film interface. This is the definition. Is clear? Now, Another thing I will discuss here, that is the isotropic and anisotropic etching. Etching may be of two different types, which is known as isotropic and anisotropic etching. In case of anisotropic etching, the etch rate in lateral direction is different from the etch rate in vertical direction. In anisotropic, in ideal anisotropic etching, no etching in lateral direction. The pattern is transferred with perfect fidelity. That means lateral direction there should not be any etch. The etch is only vertical direction. Etch rate in the vertical direction is maximum. Etch rate in lateral direction is 0. That is the anisotropic etching. So that means you will get perfectly vertical wall, and if it is so, then what should be the bias? Should be 0, because in that case df and dm will be the same value, because laterally there is no etch, isn't it? So then bias will be 0. That is in case of anisotropic etching. And the next one is isotropic etching. And in isotropic etching, vertical and lateral etch rates are equal. Etch rate is independent of direction of etching. Whether etching is directed vertically or it is directed laterally, etch rate will remain same. So in case of isotropic etching, the etch profile appears to be a quarter circle after etching. In this particular case, bias will be 2 into the film thickness. And that case we described in earlier diagram. The bias equal to 2 into film thickness, that is in case of isotropic etching. And you have seen there in the earlier view graph, you see it is some type of semicircle. You see, part of a circle, quarter circle. If you look into here, this is a circle point, so it is a part of a quarter circle. This side similarly is a point here, so it is a quarter circle. So that is undercut this, and that undercut will be equal to the thickness of the film. So these are isotropic and anisotropic etching. And the examples are, in case of liquid, both. In a liquid etchant, maybe isotropic and maybe anisotropic. In dry etching, maybe isotropic, maybe anisotropic. In normal liquid etching, which we use in case of removal of silicon dioxide using buffer hydrofluoric acid, that is the example of isotropic etching, because there the lateral and vertical etch rate will be there. So that means undercut will be there. But there are certain etching solution which can etch a particular film in a particular direction, direction dependent etching. For example, I am telling you liquid etchant. One is a etching of silicon using KOH, potassium hydroxide. Potassium hydroxide is an etchant of silicon, not silicon dioxide. So if the potassium hydroxide is used for removal of silicon, and this particular solution etches single crystal silicon at different etch rate in different orientation. That means if 100 silicon if you take, so it etches 100 in a higher rate compared to the face of 111 or 110. That is direction dependent etchant. And if it is so, then you can easily form a V group in silicon by using the QH, because vertically it etches and laterally it does not etch. So you can have a V group type of thing. This is liquid etchant anisotropic, direction dependent etchant. Okay. So let me stop here. Next class we will discuss further on isotropic and anisotropic etchant and degree of anisotropy, etc.